Hey everybody. So we're going to talk a little bit today about aisle, and we're actually going to put this through a cycle for Newton's third law, so you can see a little bit longer about the progression as to how it works. Now, the other way in which we're doing this is the idea of what's called a minds-on approach as opposed to a hands-on approach. Now, a lot of times in science, when we're talking about inquiry, we're dealing with hands-on activities and having them physically manipulate things, and that's true. And that is a lot of times what we do and how we want to teach our science. But also a lot of times we talked a little bit about how, this isn't a lecture, but we can activate our students' minds by engaging them even without actually have to physically manipulating things. And this is going to be an example to kind of show you as to how we can do that. So we're going to go ahead and get started with this minds on aisle cycle for Newton's third law. So we talked a little bit already about Newton and some of their observations and Galileo's observations. So what I want you to do is I'm going to show you two videos, and I want you to pay attention and just make a list of what do you see happening in both of the videos. Now I'm going to give you some pieces of information. Eugenia's mass with the gear is 52 kilograms, whereas David's mass with the gear is 83 kilograms. So let's go ahead and watch observation video number 1. Okay, so there's the first experiment, and now this is where Eugenia and David pull on each other. Okay, so what I want you to do now, since you're doing this at home, you probably don't have a partner to work with, but I want you to think in your head and look at the videos, and you can rewind this if you want to make as many observations about what you saw in the two videos as possible. So I want you to pause this, think about it, and write down all of your different observations. Okay, so now that you've probably written down some of your observations, typically what we get for our observations were that David moved faster than Eugenia. So that meant that David moved slower than Eugenia. Also, a lot of times we see observations are that they're always moving in an opposite direction. Now, what some people also notice is that when David pushed Eugenia, that meant that we also saw Eugenia move when she was pushing off on David. So these are some patterns that are starting to develop between the two videos. You tell me, what do you think? What are some commonalities? What can we try and determine as our model? And what are the patterns? So take a second, think about the patterns you see developing, and think about the model that we can develop from this. Okay, so one of the patterns should have been, it's usually a little bit easier to see than others, and that's the idea that when they pushed on each other, they both moved, and they moved in opposite directions. Now, if we're in elementary, you notice I gave you the mass. So you saw that Eugenia had a lower mass than David. David had the bigger mass, but David also moved slower. Now, if you were in an upper level class, you actually have the time because you know the frames and the timing of the frames per second for the video, and you also have the distances marked on the board. So not only did Eugenia move faster, but you could also calculate and see that Eugenia also had a higher acceleration. Now, if Eugenia pushed on David, we know that David moved. We know that a force is a push or a pull, so that if David was standing still, and thinking back to Newton's first law, in order for him to change what he was doing, there has to be a push or pull on David. Well, Eugenia also moved. So what does that mean? Well, that means something had a push or pull on David. And so if you actually went through and did the calculations, you could see that the force exerted on David is about the same size as the force that's exerted on Eugenia. They're just in opposite directions. In science, we call this Newton's third law, and you've probably heard it a couple different ways. I don't like for every action there's an equal and opposite reaction. What this it kind of makes you think like it's a cause and effect. If I do this, then this is going to happen. Well, no, it's a simultaneous. It's not one after the other. They happen at the same time. So whenever one object exerts a force on a second object, the second object exerts an equal and opposite force back on the first. Here's another way to think about it. If object A exerts a force on object B, then object B exerts a force on object A, equal in magnitude, but opposite in direction. So that meant that if Eugenia pushed on David with a force of 100 newtons, then that meant that David pushed back on Eugenia with the force of 100 newtons. So let's get a couple examples of this. Now, I know I said I don't like the for every action there's an equal and opposite reaction, but we can use those terms to talk about pairs. So the baseball bat exerts a force on the baseball. Well, what's the pair? Well, if the bat exerts a force on the ball, then the ball exerts a force on the bat. Think about it like if you play volleyball. If I throw the volleyball up in the air and I spike it, my arm's going to get sore because even though my arm is exerting a force on the ball exerts a force back on me. The girl's hand exerts a force on the boy's face. You write down the pair. The earth pulls a rock downward. Write down the pair on the paper. The phone resting on the desk. What's the pair? And you know me, I'm going to give you a video example. So I'm going to show you a commercial. And in this commercial, I want you to pick out a couple pairs. So you know me, I love my funny videos. I love my America's Funniest Home videos. So what I want you to do is I want you to write down one or two of the pairs of forces, how one object is exerting a force on the second object, and that second object is exerting a force back on the first. Okay? Now, let's hold up for a second. Some of you are going to be future teachers. Maybe you might be teaching this as a science. One of the most difficult things is to really understand and listen to your students. So imagine you just did the exact same task with your students, and one of your students asks you the following question. What do you say to them? But I don't get it. I understand that the earth pulls the rock downward, but if the rock pulls the earth upward with the same amount of force, why doesn't it accelerate up the same way the rock accelerates down? So I want you to pause it, think about it. What would you say to your student? Now, sometimes we can say like, well, let's look at, we'll go home, we'll talk about this, ask your parents, we'll figure it out tomorrow. It's a good question. We can do that some of the times as teachers, absolutely. I think it's great for us to admit that we don't know everything. We can't do that all the time now. So what might you say to them? Pause it, think about it, write it down. So what the kid is basically saying, what your student is saying is that, well, me as the instructor, I weigh 225 pounds. Okay, fine, 230 pounds. If that's the force of the earth pulling down on me, that also means that I'm pulling the earth upward with a force of 230 pounds. So I'm sitting in this chair, and if the chair gets pulled out from under me, I fall towards the earth, and it's going to hurt because I know it doesn't take much for me to get hurt anymore. Why doesn't the earth come up with the same rate? If you remember G, 9.8 meters per second squared, we'll talk about that. Well, the difference between me and the earth is the size. The earth is huge. Me, not so much. We're talking like the mass of the earth is like 6 times 10 to the 24th kilograms. Me, maybe like 40. So even though we exert the same size force on one another, the issue is that that same size force on the earth, the size of the earth, the acceleration is so incredibly small, you don't notice it. Now here's another situation. Here's another assessment question. How do you prove to your friend? Your students are outside playing kickball, and Dustin just learned about Newton's third law and says hogwash. He's a big Harry Potter fan. If the two forces were equal and opposite, then when I kick this ball, it shouldn't accelerate because the forces add up to zero. He then promptly kicked the ball in front of him and sees it goes rolling away. He points and says, see, I'm right. Now, how do you help Dustin understand Newton's third law? So, again, one of the most difficult things as a teacher is to really listen and understand what the students are saying and what they're trying to say in their thoughts. So, pause it, think about it. What might you say to Dustin? Okay. Well, the first thing you need to think about is looking at it from what Dustin understands and what he doesn't understand. Because in some situations, a little bit of knowledge can be a dangerous thing. And he's right in the regards of that if two forces are equal and opposite, if they add up, it shouldn't accelerate it because those forces balance. Well, that's true if those forces are acting on the same thing. But in this situation, when we're talking about Newton's third law, the forces are acting on different objects. So my force from the kick is on the ball. The force for Newton's third law is the ball on my foot. Now, if you ever played soccer, you really don't kick with your big toes. You kind of kick with the heel or off to the side because you can possibly break your toe. That's because there's the force from the ball onto your toe. And that's what Dustin is missing here. Dustin doesn't realize that those forces are acting on different objects now. Usually before this in physical science, we're always talking about forces on one object. We only have one object of interest. Well, now we have more than one because the force from my foot on the ball is one object of interest, and then the force from the ball on the foot is a second object of interest. So this is where Dustin is having a problem. So I could tell Dustin, I said, hey, it's a good theory. Let's test it. Go kick that wall as hard as you can. Now, hopefully you'd stop him and you wouldn't actually have him do this. But Dustin would have realized, like, well, no, it's going to hurt. Why does it hurt? Well, however hard I hit the wall is going to be as hard as what the wall hits me back or kick it back. So that's a way that I can kind of show to my friend, like, hey, don't do this. It's going to hurt. Now, here's an evaluation question. So Superman is actually seen above in the movie, and he's throwing the space shuttle in front of him. Now, in the next scene, so Superman's there, he's holding the space shuttle, and then he throws it forward. In the next scene, he's in the exact same position and didn't move. Now, forgetting about the movie magic of Superman can actually do this, Superman can fly, forget all that stuff. In a strict physics sense, what is wrong with this scene? Pause it, write it down. Well, if you think about it, if Superman is exerting a force on the spaceship, well, according to Newton's third law, then that means that the spaceship has to exert a force back on Superman. Well, if there's a force being exerted on Superman, that should cause him to change his position. So now that we've looked at our model, we've evaluated as teachers, we're assessing our students' ideas, but now we want to test our model. We want to test Newton's third law. So I'm going to give you 3 different experiments. So in these experiments, the first one, Eugenia and David are standing on rollerblades once more. One is holding a medicine ball, and remember, medicine balls, those really heavy balls that you pass back and forth with or do exercises with. So one of them is holding a medicine ball, then passes it to the other person who then passes it back. What should be happening in this experiment as Eugenia and David pass the medicine balls back and forth? In the second experiment, a person who's in sneakers throws a medicine ball to Eugenia who's standing still on the rollerblades. What should happen in this situation? Now, in the next experiment, and just so you know, that's Eugenia's son, so he's not going to throw it too hard to knock her out because, I'm Eugenia, don't want to hurt her. So in the third experiment, that person who's still in sneaker throws a medicine ball to Eugenia who is on rollerblades moving toward him. Now, based upon our model that we've just developed, what should happen in each of these 3 cases based upon our model? So pause it. What do you think should happen with the 3 cases? All right, so hopefully you've already written down what you would expect to happen in those three cases. So let's actually test it out. So hopefully with the first experiment, you said that, well, when the person threw it, that's when they would be speeding up. And when Eugenia were to catch it, she'll move at a constant rate. And then when she throws it back, she's going to speed up and move a little bit faster in the opposite direction. Okay. Second one. So if you notice, the person in the sneakers threw the medicine ball, and since the ground prevented him from moving, Eugenia caught the medicine ball, so there was a force exerted on her, causing her to move backwards. Then the last one. So hopefully what you saw happening in your prediction was once she caught the medicine ball, it would actually slow her down, which is indeed what happened. Because remember, we want our testing experiments to be different than what our observation experiments were. Now, we need to think about, where does Newton's third law apply in your life? Every single day we experience physics, we experience science. So in this particular third law example, where do we see it? Well, in a lot of textbooks, when they give examples about Newton's third law, this is the type of example they give. And I'm just throwing this out there. I grew up in the country, very rural. I was a redneck growing up. I can call myself a hillbilly. That's why I love this one, because I just love the name of the hillbilly one. Okay? Rockets. Rockets are an example of Newton's third law. That's typically what we see in the classroom. And we can, see the rocket go up. The gas goes up the side, and of course this causes the rocket to propel upwards. And this one you can actually see goes up pretty high. I would be pretty scared of amateur rocket builders building a rocket that big. Um, so yeah. And the rest of it is just, again, showing it again, launching, and everyone cheering at the very end, which, again, pretty cool. Now, arguably, the most common example of Newton's third law that happens every time is, I want you to stand up, walk somewhere, walk back. That's Newton's third law. And honestly, this bothered me as a kid growing up. It's like, I'm pushing backwards on the ground, but I move in a different direction because I exert a force on the ground, which in turn, the ground exerts a force back on me. That's how we're able to walk. If I wasn't able to exert that force, I wouldn't be able to do the things that I do. So let me give you some safety examples here. Because again, when we're talking about safety, we always got to talk about this. Now, a real example, hold on, I actually already have this brought up. What am I doing? So I want you to watch the following and see, where is Newton's third law happening in place? Why does this situation happen? So the injured person is in the truck turns, and they fall. That's an example of Newton's third law. Now, another example is hydroplaning. So there's a lot of different examples. I'm just going to bring up one here where, when the car is hydroplaning like this, whether it's on ice or water, but when it's sliding, there's not enough friction. The road cannot exert a force on the car big enough to cause it to change its motion. So that's what causes the fact of, hey, the car is going to still keep going in one direction, and I don't have control of my car to be able to do what it is I need. So if it's snowing where you live, or if it's raining, you have to be careful to drive slower in these conditions, because it all deals with forces and how they're able to exert and to cause the car to change and move different directions. Or in some cases, the ability to not change what they're doing. Okay? And now the other one is, again, just don't do this at home. Let's add a little bit of levity to it. So as you can see, this is not a very safe thing to do. Because think about it. He's running towards the wall. He hits the wall. He exerts a force on the wall. The wall exerts a force back on him. They do fast motion. And they just change it around a little bit. But this is like, don't want to hit the wall. If you get mad, don't hit the wall, because you're only going to hit yourself if you do stuff like this. So you can keep watching it if you want over and over again. I'm not going to do that here. Now here's the final task, and I want you to design an experiment for this. Your following week in class, you overhear your students talking about an accident that occurred over the weekend between a large truck and a small smart car. John states that the large truck hit the small one super hard and nearly destroyed while the car barely hit the truck, causing it to only have a dented bumper. Now, Stephanie's not sure that the statement is correct. So I want you to design an experiment, anything you could possibly do to test this situation out. Well, first we got to think about what is being said. John is saying that the large truck hit the small smart car, caused a lot of damage to the small smart car, so the truck hit it super hard. Whereas the truck didn't cause any damage to the car didn't cause any damage to the truck, so the car exerted a pretty small force on the truck. Well, do we agree with that statement? Do we not? So I want you to design an experiment. Think about you had enough money to get whatever type of sensors, however you wanted to do this. How could you test that statement out? Now, a little interesting tidbit. As an instructor, I want to always promote the idea that, STEM is for everyone, science is for everyone. And sometimes, unfortunately, we view STEM as, or some people will see STEM as, oh, well, science is for boys. No, not true. Not true by the longest stretch. But as an instructor, I want to make sure I don't do anything that encourages that belief. So if you've noticed in all three of these assessments, I never have the girl who's the one doing the information correct, because I don't want to give the perception in any way, shape, or form that, oh, well, she can't do science. So if there's ever an evaluation task or something like this, I typically use, if it's, a male in a problem like this, as they're the ones that are not correct, not, to be, picking on the guys or anything like that. But I just want to make sure that we never do anything subconsciously in that regards. Okay, so I want you to pause it, write down what your experiment would look like. So now that you have your experiment, what I want to know is, would it look something like this?
Okay, so let's look at this. Now, we couldn't put force probes on these two cars. So what we did was took our carts and we made one heavy and one light, and we'll measure the forces. So here we have the carts now.
So you see what they did is they have two metal carts. We're not going to use real cars because we want to be cost effective. But the cart here on the left, you can see has extra masses on it. The cart here on the right does not. These are force probes, and they measure the size of the force. Now, if our model's still correct, even with the different sizes, this chart shows force on the y-axis and time on the x-axis. If our model's correct, what should I see happening?
You can see that this one has like twice as high as the black bars. So this one's the heavy one, this one's the light one, and they're going to hit. Oh, wow.
So if you look at the graph, look at the measure of the force. If you notice, they're about equal and they're about the same size. So this is the way that you could design the experiment to actually test out our model.
So what did you notice?
It's the same as it is when they both were the same mass.
So that was a slight example about Newton's third law. And like we said, what this was, the idea was that this is a minds on type way to teach a lesson as opposed to a hands on lesson. Everything we could have done, especially if you want to get rollerblades on, go for it. I know I will probably break my back if I do that, so I don't play rollerblades because I'm always afraid of the legs doing the split and yeah, not being all that fun. So, but this is another way that you can teach science with the minds on approach, but also looking at how it was presented. So think about all these different things, and we'll talk to you in the next video. Bye bye.